Two population parameters we are usually interested in when you're talking about hypothesis testing. You may be interested in population mean, or you may be interested in population proportion. These are the two parameters we discussed: population mean and testing of population proportion. So when we are testing population mean, we came across three types of hypotheses, three sets of hypotheses: equal, not equal, greater than or equal against less than equal against greater than. Once you formulate the hypothesis, you said you check if sigma is known or sigma is unknown. If it is known, you use z-test. If it is unknown, you use t-test. For both z and t-test, we got three approaches. We got the critical value approach. We got the p-value approach. And we got the confidence interval approach. And we said following any of these three approaches, you will always get to the same conclusion as long as alpha is same. That means if you keep alpha 5% for all three approaches, you will always reach to the same conclusion. Then we talked about testing population proportion. And again, we said we can encounter three types of questions regarding P. P equals to something against P not equals to something, greater than equal to against less than equal to against greater than. And we got just a one case, which is an approximate z-test for testing proportion. So we don't have sigma known, unknown, nothing. We just use the z-test for this one. And to be more accurate, this is an approximate z-test. And again, for this approximate z-test, we got the three approaches. We got the rejection region approach. We got the p-value approach. And we got the confidence interval approach. This was all your chapter 9. This is whole summary of chapter 9. Now, if you have any question from chapter 9, please go ahead and ask. Any minor or major point that you are not able to follow during the last lecture, you may go ahead and ask now. Okay, in case there is no question, now we talk about what is this alpha. We have been using this alpha and we have been calling it probability of type 1 error. But we never went into the details of what basically this alpha is. We assume it 5% or 10% or whatever, but we never went into the details of what this alpha is. Today I'm going to tell you what basically this alpha is. When you talk about hypothesis testing, we have noticed we always have a null hypothesis denoted by H naught. And we have an alternative hypothesis. An example of null and alternative hypothesis is like mu is 7 against mu is not 7. Just an example. I can give you an example from P. I can give you an example from known sigma case, unknown sigma case anyway. Now, look at these two hypotheses. According to the definition of hypothesis, hypothesis is a statement about the population parameter. And in this chapter, we had two parameters of interest. We discussed about testing mu and we discussed about testing proportion P. We talked about only two parameters of interest. We talked about mean and we talked about the proportion. Now, by the end of the procedure, you will either reject H naught or you will say we failed to reject H naught. You will perform a stepwise procedure on this H naught and H1. And by the end of the procedure, you will either say reject H naught or you will say fail to reject H naught. These are the two possible decisions you will make. Either you will reject H naught or you will not reject H naught. When you reject H naught, does this mean that H naught is false? Does this mean H naught is false? Anyone? I want you to participate.
No.
Anyone else?
I think so.
When we reject H naught, does this mean H naught is necessarily wrong?
No.
Is it possible that it may be right and you reject it?
Yes.
And when you fail to reject H naught, does that always mean that your H1 is correct?
No.
You may be making errors. There is always a possibility of making errors. That's what I mean. That's what Amjad was indicating by no. That means there is always a possibility of error. We never know the real situation, whether this hypothesis is right or this hypothesis is right, we will never know. Because these are statements about mu. These are statements about unknown population parameter, and you don't know these parameters. So you will never know whether mu is 7 or not. By the end of the procedure, your decision may be right, may be wrong. So there is a possibility of error, always a possibility of error. So we try to explain this whole situation in terms of a 2x2 table. Now in a 2x2 table, I'm going to write the real situation on the top, which we don't know, which we never know. The real situation can be that H naught is true, and it can be that H naught is false. Maybe mu is 7, maybe mu is not 7, which you will never know, by the way. You will never know about this one. And your decision, I'm going to write it on the x-axis. You may reject H naught You may reject H0, or you may fail to reject H0. So this gives us 4 possible situations. Those 4 possible situations are that your H0 was true and you reject it. Is it a good decision?
No.
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 No. The second situation is your H0 was false and you reject a false hypothesis. Is it a good decision?
Yes.
Yes.
Yes. The third case is your H0 was true and you said it is true.
Yes, it is good.
The
Good
best.
decision. And the fourth situation is your H0 was false, but you failed to say it is false. So out of
Not
these
good.
four rectangles, there are 2 rectangles where I have committed errors. There is this error here, and there is this error here. And in the other 2 corners, we are making the right decision. These are 2 possible errors you may make in any of the hypotheses, and these 2 errors are named as type 1 error and type 2 error. This is type 1 error, and this is type 2 error. Type 1 error is what? Type 1 error is a kind of error where an innocent H0 is in front of you and you declare it a criminal. H0 was innocent, it was true, but you declared it a criminal. And type 2 error is a kind of error where H0, a criminal, is standing in front of you and you failed to say that he is a criminal. Which one is more serious? Is it type 1 or type 2?
Type 1.
That means you declare an innocent H0 a criminal.
Yes.
What about type 2? You leave a criminal and declare him as an innocent person.
Yes. Type 1.
Is that serious also? Which one is more serious? We don't know. We don't know. Both of them are serious. In hypothesis testing, if you try to minimize the probability of one of these errors, the second one will start to go up. And if you try to minimize the second one, the first one will start going up. For example, if you are a judge and you become a very strict judge, you start sentencing almost everyone, you start declaring everyone, even with a little doubt, you start declaring them criminals. So if you are strict and you are very fond of declaring everyone criminal, what you will be making is you will be making type 1 error very frequently. Your probability of type 2 will be very small because you are almost declaring everyone. So you will not be declaring innocent to the criminals, but again your type 1 error will go high. On the other side, if you are a very lenient, very relaxed judge, in that case your type 1 error will be low. You will not be sentencing the innocent people, but you will be committing type 2 errors. It is impossible to minimize both of them at the same time. Now let's talk about the notations. What notations do we have for these 4 situations? For these 4 situations, there is type 1 error, and the probability of this type 1 error is denoted by alpha. This is your alpha that we usually fix at 5% or 10% or wherever you want. Now talk about this situation. When your H0 is true, I'm talking about this first situation. When your H naught is true, the probability of rejecting it is alpha. What is the probability of not rejecting?
Beta.
1 minus alpha.
The complement.
1 minus alpha. The complement. Similarly, the notation for this second type of error, the probability of type 2 error, is denoted by beta. So if beta is the probability of error in the second situation when H naught is actually false, what is the probability of the right decision?
1 minus beta.
1 minus beta. This gives you a 2 cross 2 table. This 1 minus beta, sometimes it's called the power, how powerful you are. Because as a judge, it needs a lot of guts to call a criminal a criminal. That is why 1 minus beta is sometimes called as the power of the test. When H naught is false, it really needs a lot of power to say that it is false. So we come across here some of the notations. One notation is alpha. What is alpha? I'll write alpha as an expression here. Alpha is the probability of rejecting H naught given H naught is true in terms of conditional probability. We come across beta, that is the probability of failing to reject H naught given H naught is false.
So the true value will be given.
I have not touched the example yet, just the notations. I'm talking about what these mean, what these terms they mean. There is 1 minus alpha. This is the probability of failing to reject H naught given H naught is true. And there is 1 minus beta. This is the probability of rejecting H naught given H naught is false. These are the 4 probabilities we come across in hypothesis testing. Now, as we said, it's almost impossible to minimize both of these errors, type 1 error and type 2 error. So what we do is we try to fix one and see how other is behaving. That is why in every question of hypothesis testing or confidence interval, what you see is the first thing we do is we fix the probability of type 1 error. We fix alpha either at 5% or 1% or 10% or whatever. So what we do is we fix the probability of type 1 error and we try to see how type 2 error is behaving. Let me give you an example here. Suppose X follow a normal distribution with mean 10 and standard deviation 2. So mu is 10, sigma is 2. From here, I pick a sample of size, let us say 25. I'll pick a sample of size 25 and I'll calculate X bar. Assuming sigma to be known, I will reject H naught. By the way, my H naught is here. My H naught is, let us say mu equals 10 against H1, that mu is not 10. I will reject H naught if my X bar is, let us say, within, no, I will reject if it is outside. If my X bar is either greater than, what should I say? Greater than, let us say, 10.5, or X bar is less than 9.5. As long as my X bar is within 9.5 and 10.5, I will say, okay, my mu is 10. I will accept it. Otherwise, if it is far away from 10, how far away? Either less than 9.5 or greater than 10.5. If that is the case, I will say I reject H0, because now X bar is deviating from mu with a significant amount. For me, significant amount is half. For you, it can be different. It can be different from person to person. This is called rejection region. Whenever there will be a question of finding alpha, the rejection region will be given. Now I can ask you to give me the alpha for this rejection region. What is alpha for this rejection region? Alpha will be probability of rejecting H0 given H0 is true. That means the probability of X bar being greater than 10.5 or X bar less than 9.5 given mu is 10. Or will become what? Probability of X bar greater than 10.5 or will become union, yes? Yes or no?
Yes.
Yes. So union, I'll use the addition theorem here and I'll open it. This will be probability of X bar greater than 10.5 given mu is 10 plus X bar less than 9.5 given mu is 10 minus the probability of X bar greater than 10.5 and X bar less than 9.5 given mu is 10. Probability of A union B is probability of A plus probability of B minus A intersection B. Now, who can comment on this last intersection probability, what it will be?
It will be 0.
Why it will be 0, Umar?
Because there is no number greater than 10.5 and less than 9.5.
Exactly. There cannot be a value of X bar that is greater than 10.5 and at the same time it is less than 9.5. So this probability will be 0. So you will have just the two cases, that is probability of X bar greater than 10.5 plus the probability of X bar less than 9.5. So it's very easy to find these probabilities. We did this in chapter 7. We standardized this one to Z. So this will be probability of X bar minus mu divided by sigma over root of n greater than 10 minus which mu am I going to use? I'm going to use mu that is conditional.
No.
10.5 minus 10. This is the mean I'm going to use. This one. Sorry. This is the mean I'm going to use. Given mu is 10. So when I'm standardizing, I'll use this mean. I'll call this one as mu naught. Divided by 2 over root of 25 plus the probability of X bar minus mu naught divided by sigma over root of n less than 9.5 minus 10 over 2 over root of 25. Conditional is gone because I have put that value of mu inside. I have put the condition already. I put mu equals 10. Now this becomes probability of Z greater than, what is it? 5 times 0.5 is 2.5 divided by 2. What is 2.5 divided by 2?
1.25.
1.25 plus the probability of Z less than minus 1.25. So greater than probability cannot be found from Z table. I have to convert this one into 1 minus probability of Z less than 1.25 plus the second one can be found directly from the Z table. So I will go to the Z table and look for probability less than minus 1.25 and less than 1.25. I'll get both of these two from the Z table and I'll plug them in here. So less than 1.25, I'll try to circulate 1.25. That is 0.8944. This is one of them. And minus 1.25 minus 1.25. That is 0.1056. 0.1056, 0.8944. So that will be equal to 0.2112. If I'm using this rejection region, X bar greater than 10.5 or X bar less than 9.5, indirectly, I'm saying my probability of type 1 error is 21.12%. That is, if H0 is true, I assume my H0 is true. Throughout, I assumed that mu is 10. So when mu is 10, and you will be picking samples from the normal distribution with mean 10 and variance 4, 21.12% of the times your X bar will be outside 9.5 and 10.5. The remaining 79% of the times it will be between 9.5 and 10.5. That's another way of interpreting this rejection region. Even when mu is 10, you can do this on Minitab. Draw the random numbers, 25 random numbers from normal distribution with mean 10 and variance 4 or standard deviation 2. Then try to find the mean of those 25 values and do this again and again and again. You will see 79% of the times your X bar will be within 9.5 and 10.5. And remaining 21% of the times it will be outside 9.5 and 10.5. That's how you find the probability of type 1 error if the rejection region is given. Yes, Ahmad Ismail.
Can you repeat the last step?
What I said is just for your interest, if you want to check this one, go to Minitab and generate a sample of size 25 from normal distribution with mean 10 and standard deviation 2 and calculate the mean of that sample. And then try to do this 100 times. Try to do this 100 times and see how many times your X bar is within 9.5 and 10.5. Out of 100 times, I expect 21 times it will be within, it will be outside, and 79% of the times it will be within.
And how we know that error?
If it is outside 9.5 and 10.5, you will say we reject H0. You will say mu is not 10, whereas you generated the numbers from mu equals 10, whereas you know mu is 10. What I'm saying is, if this is your population of X, that is normal population with mean 10 and standard deviation 2, that means mu is 10. Mu is 10. That's true. And you generate numbers from this population, 25 values, and you calculate X bar from those 25 values. So I said 79% of the times your X bar will be within 9.5 and 10.5.
How do we know that number?
This 79%, this is the complement of this alpha. That's 1 minus alpha.
Okay.
And 21% of the times, your X bar will be either bigger than 10.5 or your X bar will be less than 9.5. Almost 21%. I'm ignoring the last two decimals. So even when H naught is true, when mean is actually 10, 21% of the times you will be making wrong decisions. Let's go to the other side of the story. What if you use the same rejection region when the actual distribution of X is normal with mean 11 and standard deviation 2? Now H naught is not actually true. Let's go to the other side of the story. Your X basically follow a normal distribution with 11 and 2 square. Now your mu is not 10. Your H naught is mu is 10. And your H1 is mu is not 10. Now we can see your H naught is not true. Now if I try to find my rejection region is either X bar greater than 10.5 or X bar less than 9.5. Now if I try to find beta, because beta is what I'm finding now, beta is found under the situation when your H naught is false. So now beta will be the probability of failing to reject H naught given H1 is true, or I'll say H naught is false. That means this is the probability failing to reject H naught. When will you fail to reject H naught? When X bar is between 9.5 and 10.5. In that case, you will accept H naught. If it is outside, you will reject. Given mu is 11. Now your H naught is false. Given mu is 11. Now you will standardize according to the new mean. So when you standardize, it will be 9.5 minus 11 divided by 2 over square root of 5. X bar, I'll call it mu1 divided by sigma over root of n. So you'll get this one, probability of z between the two values. And what are those two values? 9.5 minus 11.
Minus 3.75.
Is it true? Between minus 3.75 and minus 1.5. So that will be probability of z less than minus 1.25 minus z less than minus 3.75. This one we already found, it was 0.1056, I think. Minus, what will be probability of z less than minus 3.75? Without looking into the table.
0.
0. This will be almost 0. So your beta is 0.1056. 10.56% of the times you will be making type 2 errors. Look at it for a few minutes. Give me a few minutes. I'll be back in a few minutes. You look at it and let me know when I come back if there is any question. Just give me a couple of minutes. I'll be back. Yes, any questions? Can you hear me?
Yes.
Yes.
Okay, although this is a part of lab, but let me do it for your interest quickly. I'll show you how this thing is working. I'll show you in Microsoft Excel because that is, for me, that is quicker than Minitab. In Minitab, I'll have to use the commands. In Excel, I don't need to use the commands. So I'll do it in Microsoft Excel in front of you. I'll show you this thing. Now look. In Excel, what I'm going to do is I'm going to draw a sample of size, let us say 25. So I'll generate 25 values from normal distribution with mean 10 and variance 4. With mean 10 and standard deviation 2. So there is this one number 9.79 something, and I'll generate 25 numbers. And from these 25 numbers, I'll calculate the mean X bar. That will be the mean of these 25 numbers. So the mean is 9.01, which according to our rule, we will reject H0 if our X bar is less than 9.5 or greater than 10.5. So I'm going to write an if condition here. If or my X bar is less than 9.5 or my X bar is greater than 10.5, give me a 1, otherwise give me a 0. So 1 means I rejected H0 and 0 means I failed to reject H0. So there is a 1 here, that means I rejected H0. If there is a 0 here, as you can see a 0 here, that means I failed to reject H0. Now I'm going to repeat this very large number of times and I will see what proportion of the times I'm rejecting H0 and what proportion of the times I'm not rejecting H0. So I'll do this 25 samples. I'll do this maybe 1,000,000 times. I'll drag it down to maybe 10,000 is okay. Even it's taking time for 10,000.
$3,000.
Let's go to 3,000 and stop. We'll get approximately 0.21, whatever it was. 21%. If this number that I'm generating, if it is infinity, you will exactly get 21.12. But I'm doing it only 3,000 times. 3,000 times. I did this 3,000 times. And each time, what I will do is I will calculate X bar. And each time I will apply this decision. And wherever you see 0, 0 means I fail to reject H0 and 1 means I reject H0. So I'll see how many times I rejected H0. So here, I'll sum this column and the sum is 640. Out of 3,000 times, 640 times I rejected. So to find the probability, I'll divide 640 by 3,000. What percent of the times? Almost 20.8% of the times I rejected H0, which is in line with probability of type 1 error you found. Where is it? 21% of the times. I did this only 3,000 times. That is why I'm getting approximately 21%. If I do it infinite number of times, I'll get exactly 21.12%. So although my numbers are from mean 10, the mean is actually 10, still I will be rejecting 626 times. Still I will be saying mean is not 10. If I'm using this rule that X bar is less than 9.5 and X bar is greater than 10.5. Now, on the other hand, what if my mean is actually 11? We go to the other case, beta case. I change my real situation to H1 is correct. Now I changed it, and this time I will calculate the probability that X bar is within 9.5 and 10.5. If and X bar is greater than 9.5 and it is less than 10.5. And I'll try to see the same thing. Look at this. 313% of 313 times I was unable to say I reject H0, and that is 10%. And that corresponds to this 10%. Although my mean was not 10, it was 11. Still, I failed to say that it is not 10. How many times? 10% of the times. This is what we mean by type 1 error and type 2 errors. Any question?
Sorry, Doctor.
Yes.
Is there a relation between type 1 and type 2 error?
Yes, as I said, if you try to minimize one of them, the other one will go up.
Okay.
For example, if you want to minimize the first one, what you will do is you will widen the limits. The limits are 9.5 to 10.5. If you want type 1 error to be small, you will widen the limits. If the limits are from 9 to 11, the type 1 will be small. But when the limits are wide, type 2 will go up. Do it. After the class, do this exercise and hold this. Just change here. The rejection region, make it X bar greater than 11 or X bar less than 9. Change the limits. Make the limits wide, wider than this 9.5 to 10.5. When you make them wide, what you will observe is you'll observe alpha will come down and you will observe beta will go up. Good question it was. Any other question? Okay, in case there is no question, let us start our chapter 11. Should we start?
As you like.
We have how many minutes?
12 minutes.
12 minutes. In 12 minutes, we can cover half of the chapter.
Oh, okay.
The speed with which I'm going after the midterm exam, we can.
Yes.
So now that the frequency between you guys and myself, it is set, we can afford to go fast. Okay, let us discuss something general. I'll not go into the specific details of regression. Let us discuss something general. What is a mathematical relationship? What is a mathematical relationship? Muhammad Faris.
It is like a linear or something like that. Equation. It is a linear equation or not linear. If it is linear, so it is regression.
Forget about regression. I'm not interested in regression. What is a mathematical relationship? The one I wrote in front of you, is it a mathematical relationship?
Yes.
What is the area of a circle?
R squared by
R square. Is it a mathematical relationship?
Yes, because we can substitute value.
Yes. And by the way, these are quadratic relationships. Let me give you an example of linear relationship. The linear relationship example is about the temperature, Fahrenheit. That is 1.8 times Celsius plus 32. Is that a mathematical relationship?
Yes.
If I tell you that today's temperature is this much Celsius, can you tell me exactly what is the Fahrenheit temperature of today?
Yes, we substitute by C, the value of C.
Yes, you substitute. If I tell you today's temperature is 40 degrees Celsius, you can give me the exact Fahrenheit for today. These type of relationships where we have two variables, one of them is F, one of them is C. Similarly, in a quadratic relationship above, you see one of them is area, one of them is radius. In the one above, you can see three variables. There is E, there is M, there is C. Is E a variable?
E, no. E in the first one equation.
Yeah, is that a variable E or is it 2.718 E?
Not a variable, it is a value.
Okay, okay. So there are again two variables in the first equation. There can be more than two variables. Yes, Ahmed?
It is a variable. It's not the E 2.71.
It's not. Yeah, this is what I thought. It's not 2.718. It's, I think, a variable. What is it? E for it's something. E is another variable. So that relationship is among three variables, not two variables. A quadratic relationship between three variables. Then we have a quadratic relationship between two variables. Then we have a linear relationship between the two variables. What is the property that makes them mathematical relationships? What is the thing that makes them mathematical relationships? The thing that they are exact. This makes them mathematical relationships. If I give you the value of Celsius, you can give me the exact value of Fahrenheit. If I give you the value of radius of a circle, you can give me the exact area of the circle. If I give you the value of C and M, mass is M is mass, C is I don't know what. If I give you M and C, you can give me exact value of E. So this property of these relationships, that if I give you the right side, you can give me the exact value of the left side. This property makes them mathematical relationship. Mathematical relationships are always exact. On the other side, we have some variables where we think that there is some relationship, but it's not exact. For example, I define X as the monthly expenditures. And I define Y as the monthly income. Now, for a person whose monthly income is more, what do you expect about the monthly expenditures?
Sorry, could you repeat your question?
If I tell you that there is a family whose monthly income is, let us say, 15,000 riyals, what do you expect from the monthly expenditures?
To be high.
Less than 15,000.
Less than 15, somewhere around 12, 11, 10, 9, somewhere around this.
Yes.
But if I tell you there is a family whose monthly income is 2,000 riyal, what do you expect their monthly expenditures?
Less than 2,000.
Somewhere around 1,500, 1,800, 1,900, maybe sometimes 2,100. Sometimes they may go in loss more than 2,000. So if I give you the income of a family, you have a rough idea about their expenditures, but you cannot give me their exact expenditures. We can feel there is something going on between the two variables, but it is not exact. These type of relationships are called statistical relationships. When you can feel there is something theoretically between the two variables, but you don't know what it is, and you're trying to identify what it is. This thing is called statistical relationship, and when you try to come up with an equation that gives you the relationship between these two variables, that equation is called regression. And how do we do that? We do what we do in statistics. We collect some data, and based on that data, we try to estimate the line. We try to estimate the relationship. Because we cannot have the exact relationship, so we come up with an estimated relationship. So this chapter 11 is about regression, where we will make some assumptions. The first assumption is that the relationship is among only two variables. There is one variable on the right side, one variable on the left side. It is similar to this Fahrenheit and Celsius. There are no two variables on the right side. Later in chapter 12, we will let go of this assumption and we will try to see the relationship between more than two variables. So chapter 11 is assuming that there are only two variables. This is called simple regression. When you will have more than one variables on the right side, you will call it multiple regression. That will be covered in chapter 12. Another assumption we are making that the relationship is linear. So keeping these two assumptions in mind, the name of chapter 11 is simple linear regression. You'll be assuming that there are only two variables under the study, and you'll be assuming that the relationship among them is a linear relationship. So you'll be trying to estimate something like this. Let me change the names of these one. Income is X and expenditures is Y. So you'll be trying to estimate a line like this one. Y estimated equals the intercept plus the slope times X. So you'll be trying to estimate this beta naught and beta 1. We can see that there is a relationship between X and Y, and this is the relationship between X and Y. And because it is not exact, I will add error here, plus or minus something. This epsilon can be plus or minus something. Unlike the mathematical relationship, in the mathematical relationship, I would write that Y equals beta naught plus beta 1 X, no epsilon. This epsilon term makes the relationship a statistical relationship. This epsilon says that the expenditures are something plus something times income plus or minus something, which this plus or minus something is unknown to us. So what the objective of next class will be, we will be trying to estimate these two parameters using the data. Exact same thing that we have been doing until now. We have always one parameter mu. We try to estimate it using X bar, and then we create its confidence interval, and then we try to do hypothesis testing regarding mu. Same thing we will follow here, but here the only difference is you have a couple of parameters, not one. You have two now at the same time. You have beta naught and you have beta 1. The first thing you will do is you will obtain the pairwise data on X and Y. From there, I'll give you the formulas. You will estimate beta naught and beta 1 by their estimates, beta naught hat and beta 1 hat. This is like estimating mu using X bar. Once you have beta naught hat and beta 1 hat, then you will try to create the confidence intervals and hypothesis testing and all that. We'll do this in the next class. I'll stop here. This was a general introduction that we are going to do. Ahmed, please go ahead.
Epsilon will be always unknown here.
Epsilon is always unknown. Epsilon is the thing that makes it a statistical relationship. In absence of epsilon, you will see it will become an exact relationship. So in case you have no questions, you can leave the session now. I will see you inshallah after the break, and from my side I will say advanced Eid Mubarak, and see you after the break inshallah.
Mubarak and take care, doctor.
Thank you very much. Assalamu alaikum.
Thank you.